Cool. Thanks, everyone. First of all, I'd like to thank Muli, John, Sartora, Stanford for organizing a great event. It's so nice to see so many familiar faces in this room. It's been quite a long time. My name is Mehdi. I'm a co-founder and director of Sigma Prime. I'm here to talk to you guys about our favorite DeFi-related vulnerabilities. Quick word about who we are for those of you who don't know us. We're an information security consultancy spread across the world. We're headquartered in Sydney, Australia, where I'm based. We are a collective of security researchers, academics, developers, all working on blockchain tech. We obviously do security assessments, that's why I'm here, do a bunch of EVM and non-EVM smart contract reviews, but we're also very comfortable diving deeper into the blockchain stack. We review consensus mechanisms, new cryptographic primitives, new networking stacks and whatnot. As you can imagine, lots of layer 2 work has been happening lately, keeping us very busy. We're also very, very keen on fuzzing stuff. Coverage-guided, white box structural fuzzing is something that we really, really enjoy. And lately, we've been doing a bunch of red teaming and social engineering exercises targeting DAOs and blockchain institutions. That's super fun. So that's kind of half of what we do. And that's the arm of the business that I look after, but we're also known as the maintainers of Lighthouse, as Mehdi was saying. So who's here excited about the merge? Oh, okay, cool. Who here runs an Ethereum validator? Oh yeah, I expected a few more hands, but that's okay. So yeah, Lighthouse has been is the Rust implementation of the Ethereum consensus protocol. We've been working on this really hard for the past 4 years. The merge is around the corner, 2.5 weeks. Super exciting. A lot of sweats and tears have gone into this, and it is happening, despite what many other people could be telling you on Twitter. It is definitely happening. So it's in Rust. So it's free. It's open source. We see this as a public good. It's heavily focused on security, and it's pretty fast. I've mentioned, obviously, that we perform security assessments. We are blockchain agnostic, per se, but a lot of the work that we do is on Ethereum for a bunch of reasons. I'll put up some of our clients' logos. I'm sure some of them are familiar to you all. And actually, there's a few of you guys in the room today, so thanks for trusting us with your security assessment requirements. So yeah, I reached out to my team and I said, hey, pitch me your favorite DeFi vuln that you've found over the past couple of years. And I've collected a whole bunch of answers. Unfortunately, I'm not too sure how my colleagues deal with this, but a lot of our work is under NDA. So we can only publish, I don't know, if I had to estimate, perhaps about 40% of the work that we do. So I'll be tiptoeing a lot during this talk. Pardon me, but hopefully some of them are interesting to the audience. A type of bug that we have been finding, unfortunately, quite often is related to typos. So this is a fun example. This is, from what I think I know, is the very first yield farming contract on Ethereum. This was developed in 2019 for Synthetics, and Synthetics got us to audit it, and it's been fun. We've done a bunch of work with these guys. For those of you who don't know Synthetics, it's a synthetic asset protocol. You basically stake SNX, the native token of the protocol, and you can mint any asset, ETH, SETH, SUSD, SAUD, STesla, SApple, or whatever. So they kind of needed a way of incentivizing liquidity providers to maintain those pegs. And this is the first iteration of what came on to be this massive DeFi farming craziness that we've noticed over the past few years. So perhaps I should maybe spend some time on explaining how we perform our reviews. All our security assessments for smart contracts are always a two-step process. So our clients come to us, they give us our target, we go off and do what we do best, come back with a report, a V1 of the report, and then they decide to fix stuff or not. At that point, they come back to us with a V2 of their protocol, and then we kick off what we call the retesting phase. And the retesting phase is there for two reasons. A, making sure that the fixes are efficient, they do indeed mitigate the underlying root cause, and B, they don't introduce new bugs. In this case, the protocol gave us an archive. This is quite important. A zip archive containing the code base in both cases, so 2 zip archives. And we basically kind of go through the audit report had integer overflows. Back then, we didn't have that protection baked into Solidity, a couple of reentrancies. Anyway, stuff that was quite common back then, and still common these days, to be honest. But yeah, so kind of running through the code line by line, making sure that those fixes are effective, they do fix the bugs. And something I forgot to mention is that we always write our own tests. We do not trust our client's tests. This is a big thing for us. We write our own unit test as part of our reviews. We typically use Brownie, even though we've been dabbling a lot with Foundry lately. Kudos to Georgios, I'm not sure if he's here, and the Paradigm folks for creating such a great testing framework. So I go back home, go back through the code base. My guys had performed the retesting. Everything seemed fine, and I run the tests again, and now those tests fail. I'm like, this is strange. Run them again, they fail again. 3 times they keep failing. I'm like, this is sus. And obviously had to start looking into this very deeply and noticed that the client had actually introduced or had shifted a closing bracket, effectively changing the order of operations. It's extremely easy to spot now, right, when you have a clean GitHub diff UI. But trust me, without this, it's very, very easy to miss. And this is the reason why, again, we write our own tests. These things happen quite often, unfortunately. Another type of vulnerabilities that my team really enjoyed finding that has been covered, I believe, by one of my peers earlier, is an uninitialized implementation contract in the context of proxies. So proxies, you've got a proxy contract making delegate calls to an implementation contract. The proxy contract typically contains account balances, the state storage, admin ownership information, and a whole bunch of statefulness. And the implementation contract is where the developers are actually building the logic of whatever protocol they're responsible for. In the context of, I think someone actually spoke about this earlier, so I'll go fairly quickly. In a lot of cases, people forget to initialize the implementation contract. That alone may not be really, really bad itself, but if you can get the implementation contract to make a delegate call to an attacking contract that you control that would self-destruct, well, you get the gist. No more implementation contract. The implementation contract is gone, and that can lead to not necessarily loss of funds, but as Emilio was saying earlier, potentially a disruption of the protocol. So we spotted this in a whole bunch of protocols over the past few years, and I believe the largest bug bounty ever given was for typically this type of bug. It was $10 million paid out by Wormhole, I believe, through Immunify last year or 2 years ago. Cool. Another type of bugs that we like finding in DeFi protocols is related to how popular swapping contracts, see the tiptoeing here, is deal with internal accounting, right? So they always have to build their own, way of calculating rewards and penalties, and a lot of them introduce the concepts of shares. They deal with shares, but they also deal with amounts. And if you juggle between the two, it's very, very easy to get things wrong. And we've raised a bunch of critical vulnerabilities related to this. Another thing related to the internal accounting is rounding errors or dust that can be left into the contract. This may not sound too bad, but it can actually render the whole protocol useless. Also, if you can manipulate the contract balance of a certain token and the developers are making assumptions on the balance of the token contract, you're going to have a bad time. Unsafe casting is also a favorite of mine, particularly when you're dealing with negative prices. So you have signed integers being casted back to unsigned integers. If you don't do this carefully, you are going to have a bad time. So poor accounting can definitely lead to funds being stuck. Another type of issues that I thought was quite interesting, because I don't think we've covered this a lot over the past few months, is related to deployments. And specifically, deployments that cannot be done atomically, right? So complex protocols, I can actually talk about this one. Rocket Pool. Who knows Rocket Pool here? Who's heard of Rocket Pool? Yeah, cool. So it's a decentralized liquid staking protocol for the Ethereum beacon chain, and it's a fairly complex protocol. 26, 28 contracts to be deployed, hundreds of EVM calls to be made for it to be set up properly in a functioning state. There's no way you can fit this into the block gas limit. No way. You could optimize the hell out of it. You can get Transmissions 11 to spend his nights on it. It's not going to happen. So you cannot have, unfortunately, atomic deployments, even if you're using factories. And this actually matters in a competitive environment. Back when the beacon chain was launching, everyone was rushing to be the first liquid staking protocol to attract as many users, as much liquidity as possible. So what happens in this case, the developers are deploying contracts, contract A, B, C, and D, and the competitor is attentively watching the mempool. And what they're going to be doing is scripting very easily a way to hijack the deployment process, or the initialization process, actually. So you kind of need to link all these contracts together, obviously, for the whole thing to work. And the attacker here is simply deploying a malicious contract and sneaking in the transaction that will link contract C with the malicious contract. And this is all automated, so it'll be a serious pain for the development team to actually get their protocol out there. We've been reviewing a lot of smart contract wallets or smart wallets over the past few years. Always fun. The standard issue that unfortunately we've been seeing too many times is the classic replay attack, right? Like in this case, Bob wants to send 1 Ether to Alice, sends that transaction to the smart contract wallet. First, obviously, gets the data blob, signs it with his private key, submits that to the smart contract wallet, and you're not using a nonce. So Alice can simply just use the signature, the same data blob, send that to the smart contract wallet, and keep doing this and draining Bob's balance. More recently, protocols have been toying with novel cryptographic primitives to essentially try to lower the cost of doing multi-sig. And BLS is one of the primitives that has been used lately, and BLS is great. We actually use this a lot on the Ethereum consensus side of things, and this is why we can have an Ethereum beacon chain that can support hundreds of thousands, millions, tens of millions of users. And the way it works is thanks to BLS aggregation. So I can actually get a collection of messages signed by different parties, aggregate those messages into one single message, verify the signature, the aggregated signature for that message, and have the mathematical insurance that all of those messages have actually been signed properly by the different validators. So this is great. However, if you are to implement this naively, you are most likely going to be vulnerable to this thing called the rogue public key attack that's been documented by Dan Bonnet and a bunch of other people. Dan Bonnet, the B is the B in BLS, those of you who don't know. And it's really, really, really clever, and it's not actually that hard. So the aggregated public key, you should just see it as the sum of all the public keys used to compose the aggregation. So what if I can come in and be part of those messages, and I can pick my own public key so that it negates all the other public keys so that I can have an aggregated public key of 0? Well, fun times, because now you have a signature that is effectively pointing to the point at infinity. So you basically can vouch for any message, verify any message. Your contract that's going to verify the signature is going to verify, is going to be, okay, yeah, you're sweet, no worries, let's go. And you basically can take over any wallet that uses this. And we found this very recently. The report is not public yet, but I'm very, very grateful and hopeful that it will be in the next few weeks. So stay tuned for hopefully a blog post explaining this. Merkle proofs mishandling. Merkle proofs, sorry, probably need no introductions, but let's just say that they're a way to prove the inclusion of a certain element in a tree, and they're used kind of everywhere these days in the blockchain space, particularly in Ethereum. I'm going to need you to conceptualize things with me. So let's say you have a bridge, right? A bridge that is kind of responsible for linking a side chain and Ethereum main chain. You have a contract sitting there, and that contract is basically representing using a Merkle tree to pack transactions. So transactions are grouped in a Merkle tree, and anyone can execute these transactions by providing a proof and a path. Those two elements are meant to represent a leaf in the tree, or therefore a transaction, a valid transaction. Now, the path essentially tells us whether we should be hashing from right to left or left to right. Okay, so I can give you the proof, but I can't. If I don't tell you how to hash it, probably not gonna be that useful. Furthermore, in this particular instance, the path was actually used to record whether a transaction had already been executed in the past, okay? So for a transaction to be executed, you need obviously two conditions. You need it to exist, and you need it to, not have been executed. So the problem here is that this variable was a bitmap. So just like a uint256, right? And used as a bitmap. I'm sure you can see the problem. Well, actually, it's written up here. If the tree is of less depth of 256, you can come up with multiple different paths that will effectively point to the same transaction. So yeah, you basically are vulnerable to replay attacks, and you can come up with different ways representing the exact same transaction. And because the path is what is used to represent whether a transaction has been spent or not, you can drain the contract of its balance. Last but not least, we've been talking a lot about EVM stuff, about Solidity stuff today, but DeFi does not solely, DeFi security is not just about EVM security, right? Bunch of examples, like people have been talking about rollups and WBTC and whatnot. There's off-chain components to the whole thing, right? I said that we love fuzzing stuff, and we particularly enjoy fuzzing serialization. That's like, if you talk to anyone who's keen into fuzzing, it's like the first thing that you'll target. It's like, okay, cool. You come up with your own marshalling system, I'm going to hit that first. And we do obviously coverage-guided, instrumented structural fuzzing. That yields usually great results. And sometimes the bugs we find are more interesting than what we anticipate. I'd like to introduce you all to Skippy Peanut Butter Bug, which is CVE 2021-3121, which was identified last year by Kirk from my team. It targets GoGo Protobuf. GoGo Protobuf is a very popular library used by a whole bunch of projects, including Docker, Kubernetes, and a bunch of others. So it made for a very interesting disclosure process. 9.8 was the severity given by Mitre, and Mitre were the ones actually calling it Skippy, and they called it Skippy because the actual variable at fault is named Skippy. Anyway, little joke from these guys. Didn't know they were that funny, but yeah. And the cause here is an integer overflow that leads to an index out of bounds that obviously leads to a panic. And in this context, you can basically craft one single packet and send it to this validator or relayer in this instance, and the node would go down. It's great. It's even better when the peer-to-peer propagation happens before the deserialization. So you basically feed one node a packet, your malicious packet. That node is going to send it to its peer. That peer is going to send it to its neighbor. And you basically take the entire network down with a single packet. Good times. Yeah, that's about it, really. That's all I had. And hopefully you enjoyed this. I'll be around for the panel if you have any questions. Thank you.